Hi everyone, I'm Xavier Geoffrey. I'm working at Atos in the HPC and quantum business line as a pre-sales, and I'm more focused on quantum projects. Today, with my colleague Satya, we will looking at how to accelerate research for quantum applications using GPUs. So first, as an introduction, we will look at why quantum computing is so important nowadays, and especially in the era we call the NISQ era, and why specifically variational quantum algorithms are key for for the applications. Then we will have a look at what Atos is specifically doing in that domain. Then in the third part, Satya will give you more technical details on how we accelerate with GPUs quantum simulations. And in conclusions, we will look how you could yourself contribute to this initiative. So let's start on why quantum computing is so important. In fact, quantum computing relies on one premise today, is when quantum processors or quantum computers become available in the near future, they will be able to solve larger and more complex problems faster than the current most powerful HPC systems today. That means that some problems are so complex that they are currently intractable to classical computers, but will become accessible for quantum processors when they are available. So if we look at the history of quantum computing, if we show a brief overview, you can divide it in three phases. First phase, I started maybe 4 decades ago. It was really a theoretical phase dedicated to research. It has started with the first design of a quantum computer, and many algorithmic research was led, and some very famous algorithm like the Peter-Shor's algorithm that was published in 1994 regarding the factorization of large semi-prime numbers. And during all that phase, many applications were studied from a theoretical point of view, as there were no real hardware implementation that could support large algorithms. Things have started to change a few years ago with the advent of new processors, or at least at the moment we have prototypes just coming out of the labs. We call these prototypes NISQ devices. NISQ stands for Noisy Intermediate Scale Quantum Devices. Because they are noisy, they are sensitive to noise, so that means that the qubit are subject to decoherence. They are intermediate scale in the sense that they are not very scalable in terms of qubits. At the moment, we are limited to a few dozens of qubits. We can expect in the short term to have maybe a few hundreds of them, but still they are quite limited. Nevertheless, even with noisy and limited in scalability processors, we do believe that you can already solve some problems with them. And we expect that in the time frame of 2022-2023, this NISQ processor will be more widely available. And then the third phase, which is the phase about a general purpose quantum computer or fault-tolerant quantum computer, is something that will happen in the longer term, maybe in 10 or 15 or even maybe 20 years. In fact, there is no real consensus on when or even if such a computer will become available. At this time, we hope to have maybe millions of qubits, and I would say some kind of perfect qubits. That means that they are no more sensitive to noise and decoherence. Okay, as I said, the first phase of quantum history was really focused on finding new algorithms that are really well suited for quantum computers. and many algorithms, dozens or even hundreds of algorithms have been written and proven to be faster than their classical counterparts. So some of them provide a significant speed advantage, like Shor has demonstrated. Other are providing more moderate speed advantage. But if you look at moderate speed advantage and you apply it to a large use case with a large data set, this moderate speed advantage ends up with a significant speed up. So what we see is we expect some very specific algorithm to benefit from a quantum acceleration, and in that sense, quantum processor will not replace classical processor, but will be used for some specific task, for some specific algorithms, and quantum computing will be used as an accelerator of classical computing. Okay, all these algorithms can be applied to a broad range of business use cases, and as you can see here, we can find quantum speedup for use cases in nearly every industries and services. And all these use cases can be grouped into several categories. So one of the category is a quantum machine learning. So we use a quantum algorithm to speed up the training of a model, and the accelerating machine learning can be beneficial for all machine learning use cases. We have also algorithm to solve combinatorial optimization problems. So these problems are also very widespread, coming from our logistics to portfolio optimization to flight scheduling or route navigation. You have application in cybersecurity. We have already talked about Peter Shor's algorithm that can be used to do some cryptanalysis. So cryptography is a significant part of the possible application for quantum speedup. Chemistry is also a very hot topic, and you can use quantum algorithm to help you find new materials like batteries or polymers. You can use also to find new medicine. You have application more specific for the finance and financial insurance services. You have application in the oil and gas industry as well. But what is important to understand that all these applications will not be available at the same time. So we expect that some of them, like quantum chemistry, will be available in a shorter time frame. And that's mainly because we do have today the algorithms that are ready. They do not require necessarily a huge number of qubits, so they are well suited for NISQ processors. On the other hand, if you look at cybersecurity, for example, the algorithms today require a huge number of qubits and perfect qubits, so this is not expected to be available before 10 to 15 years. So if we focus now on the NISQ processors and the algorithms that are well suited for them, we have a complete class of algorithms called the variational quantum algorithms. So basically how a variational quantum algorithm is working, it's an algorithm which is hybrid between classical and quantum computing. You have a cost function that is implemented in a quantum circuit, and the goal of the algorithm is to minimize the cost of this function by classical optimizers. So you have a loop with several iterations between a quantum circuit and a classical program. So each time you loop, you modify slightly the input parameters of the quantum circuit, the angle of your variational algorithm, and then measure the cost as an output. And if you consider the cost is low enough, you can provide the results. But to provide a significantly good result, most of the time the variational algorithm require a lot of iterations, maybe hundreds of iterations before a convergence. And what is interesting, if I make the link between those algorithms and the use cases I've talked before, we can find such algorithms to solve combinatorial optimization problems like QAWA, the quantum approximate optimization algorithm. It can be used to solve many of NP-complete problems like maximum cut in a graph, coloring a graph, partitioning a graph, or partitioning numbers. We have also in the field of quantum chemistry variational algorithm, and a famous one is the variational quantum eigensolver, VQE, that is used to find the ground state energy of a molecule. And that's particularly interesting because when you have this ground state energy level, you can derive many properties of the molecule. So this is really helpful to define, to try to find a new molecule with interesting properties. You can also apply variational algorithms to cybersecurity, for example, to factor large semi-prime numbers like Shor algorithm, but you do it in a variational way. And you have also a variational algorithm that can be applied to machine learning, and that can provide some classifiers using variational algorithms. So to conclude this introduction, I would say investing in quantum computing now is important because first, we see that the quantum processor will become available soon in a 2 to 3 years time frame. Second, we do have already a lot of algorithms that exist to solve, I would say, classical problems, and we do have simulation capabilities that helps you to already adapt those algorithms to solve specific use cases, and you can implement them on simulators and run them at least on with toy problems on real hardware. But when the full hardware is available in 2 to 3 years, you will be ready if you start now programming with a quantum simulator. So to address the NISQ era challenges, Atos has put in place a full quantum program. So we have started this program a few years ago in 2016, and the program was aimed at helping people getting acquainted with a quantum computing, learn how to program, develop application and algorithms, and experiment those application and algorithms on a simulated hardware. So to be ready when the physical machine are available. So this quantum program relies on 5 pillars. So the first pillar is a programming platform. This is the Atos QLM. This is a platform aimed at program, compile, simulate circuits. So to do learning, education, research. Second pillar is about our consulting expertise. So we have a full team of experts that can identify business use cases and translate those business use cases into quantum algorithms and find the right algorithms to solve this problem and implement those algorithms in our simulator. The third pillar is about providing a new hardware. So Atos is committed in 2023 to have in its portfolio a quantum accelerator. Fourth pillar, we have a team of people working on algorithms, and more specifically on variational algorithms, as you understood, that are very well suited for the NISQ era. And fifth pillar, as we are a cybersecurity company providing hardware security modules and so on, we are developing next generation quantum algorithm for cryptography. So we were talking about quantum safe cryptography, so cryptography algorithms that are safe to quantum attacks. Here you have an overview of what Atos is proposing as a solution. So first, on your left, you have the programming environment. It's MyQLM. It's a freeware, so it's freely available by anyone that would like to know how to program quantum circuits. You can simulate the circuits. We provide a lot of tutorials. We provide a lot of plugins, for example, to interoperate with other frameworks. We provide plugins to do entry-level simulation and optimization. And depending on how much memory you have on your laptop or on your workstation, you can scale around 20 qubits. If you want to do higher level of simulation, you can use the Atos QLM. The Atos QLM is really, the quantum learning machine is really the cornerstone of our offer. It can be used by several users. You can do advanced simulation with different kind of simulator and some noise modeling, and you can scale up to 41 qubits. And really the key of the Atos QLM is performance. And you will see in the next chapter how GPU is helping us providing the best performance for simulation. And on the right, if you want to go even further, you can interface the Atos QLM with any existing quantum hardware. And no matter which technology it is, it can be superconducting qubits or trapped ions or even other technology like photons or silicon qubits, you are able to simulate on the Atos QLM and compare your simulation if you want to run the results of the simulation or run the circuit on real hardware. So really, we do have a simulation approach that is a complement to the hardware approach. The hardware approach, if you use it only the hardware approach, you have a lot of constraint. If you look at today, a quantum processor, most of them are running at very low temperature, typically a few millikelvins. They require a huge infrastructure. So this is really difficult to acquire one of them, and most of them are only accessible through the cloud. As I said, there are many technologies today providing qubits, like superconducting qubits or trapped ions, and this is not very clear at the moment which technology will be the leader in terms of stability, in terms of scalability, and clearly investing in hardware now is probably a little sooner. So you probably need to wait a little bit that the market evolves. On the other hand, if you're doing simulation, you can develop new application without any of these hardware constraints. You don't have to deal with what is the topology of your qubits, what is the gates that are available. You write your circuit in a universal way with my QLM, and the Atos QLM is translating it into the hardware that you are targeting. So that means that you, with the same algorithm, you are able to simulate how this algorithm will behave on different hardware technology. Even if you integrate noise, you can see if some hardware implementation are best suited for a kind of algorithm. So you can completely characterize, predict, and verify the results given by the quantum processor. And last but not least, as I said, most of the hardware available today can be used through a pay-per-use model in the cloud, and you have some examples here coming from the Amazon public website, and you have a price per task that is less than $1, and that is relatively small, and after that a per shot price which is in the order of magnitude of a cent. So it looks like running programs, quantum programs in the cloud is very cheap. But remember, we have seen today the most prominent algorithms are variational algorithm that requires to iterate. So you have to run hundreds of shots just to get one result. And probably when you conduct a full study, you will need hundreds or maybe thousands of those results. So if you multiply thousands of results by hundreds of iteration by a few cents, at the end you may end up with some significant investment and operational expenses. So Now, I let my colleague Satya explain you in much technical details how we use GPUs to accelerate quantum simulation. Thank you.
Thanks, Javier. Hi, everyone. I'm Satya. I'm a software engineer in the Atos Quantum Lab. Xavier mentioned earlier about the importance of a quantum emulator in today's context. So in this part of the talk, I'm going to present one of the simulators that we developed in our team, and I'll discuss how we accelerated using GPU technology. To begin with, there are two approaches to quantum computing, digital and analog quantum computing. In the digital quantum computing, we describe any complex algorithm using a sequence of gates that we call circuits. It's very similar to how the classical computers work. Typically, these gates involve one or two qubits. If the set of gates that we are allowed to execute is universal, we can then program the quantum computer to do any physically possible transformation or any unitary transformation. On the contrary, in the analog case, we express the computation by specifying how the qubits interact with each other over the course of time. During the computation, these interactions typically involve more than two qubits. Unlike the digital case, analog quantum systems are special purpose quantum computers that are very good at solving specific problems that closely resemble the underlying physical system. Analog quantum computer is harder to simulate on a classical computer than a digital one due to the presence of these multi-qubit interactions. High performance simulators for the digital quantum computation are very well known. So today I'm going to present our work on a simulator for analog quantum computation. Let me introduce you the kind of computational problems we need to solve in order to address analog quantum computing. We need two things. First, we need to specify the interactions between qubits. Second, we need to track how the qubits evolve over time. In quantum physics, these interactions are represented by matrices, and the state of qubits is represented either by a vector or a matrix, depending on whether we are modeling a perfect qubit or a noisy one. But the problem is the sizes of these matrices and vectors increase exponentially with the number of qubits. This puts a very serious limit on the number of qubits we can actually simulate even on HPC systems. To give you an idea of the memory requirements, for an n qubit state, we need to store 2 to the n complex values to describe the qubits, and 4 to the n values to store the interactions. Often, the matrix to specify the problem is very sparse, and we can reduce the memory footprint by exploiting the sparse nature of the problem. Nevertheless, the size of the resulting sparse matrix also grows exponentially. In order to describe the evolution of an ideal system, that is the system that's made of perfect qubits, we need to solve the familiar Schrodinger equation. Simulating a system with noisy qubits is a bit more involved compared to the perfect qubits. So essentially, in order to describe analog quantum systems, we need to solve a very high dimensional ordinary differential equation. Two popular software packages provide the necessary tools to study analog quantum systems. The first one is QTIP, which is a well-known Python project that started in 2011. The second one is Quantum Optics, a relatively recent module that is available in Julia. There are some limitations to these tools. First of all, these two software packages provide a single core CPU implementation. Therefore, they are very slow to work with given the problem sizes that we typically address in analog quantum computing. So in order to speed up simulations, we need a multi-core CPU implementation or even a GPU implementation. Secondly, these implementations are not efficient or not memory efficient at all. Here is a plot of the total memory requirements to solve the differential equations when the interactions are present among all the qubits. If we port these differential equations naively to run on a high-end GPU, we may not solve systems with more than 15 qubits. We can probably push this limit up to 20-21 qubits if we use a sparse representation. However, 20 qubit analog quantum systems were already demonstrated experimentally, and we would like to simulate even larger systems in order to explore near-term quantum applications on these devices. So, in order to help all these studies, we need a very fast, memory efficient and scalable ODE solver that runs on a GPU. We addressed these problems by developing an in-house simulator for the needs of analog quantum computation. First, we reduced the memory footprint by not storing in memory the matrices that specify the interactions among qubits. These matrices have a very special structure that allow us to compute the non-zero elements and their positions on the fly just by doing few elementary bitwise operations. The plot here shows the memory requirements of our approach compared to the two approaches that we've seen before. Second, in order to develop a fast simulator, the right-hand side of the differential equations needs to be implemented very efficiently. So we have implemented a very custom sparse matrix vector product that takes into account the specificity of this kind of problems. All the codes were written in a generic templated C++ code using Thrust. As for the ODE solver, we used Boost ODE int, which is also a C++ templated library that is compatible with Thrust. So thanks to these choices of these two libraries, we could generate code that is compatible with multi-core CPU architecture or GPU using a single source code just by doing a few minor modifications. So with all these developments, we were able to simulate up to 29 qubits or 30 qubits if we use single precision on NVIDIA Volta 100S GPU in a very reasonable amount of time. Here, I'm going to present the performance we obtained using our simulator. In particular, we compare the performance of our simulator with QTIP and quantum optics. So here we benchmarked random instances of analog quantum computations that randomly couple all qubits present in the system. So in this benchmark, we increase the size of system, that is the number of qubits, by fixing the duration over which we evolve them constant, and we simply measure the total simulation time. So as you can see, the computational time increases drastically for QTIP and quantum optics, which is expected because they are single core implementations. And if we look at the specific case, for example, of 17 qubit simulation, a highly parallel CPU implementation that we developed already gives a boost of 47.5 compared to QTIP, and the GPU implementation can speed it up by another 3.5 times. So that's quite interesting. And as we increase the number of qubits, the gain of using GPU over a Xeon processor becomes rather clear. The precise gain factors, of course, depend on the details of what's being computed and what's being simulated. At least in this benchmark, we observe a speed of up to 10. If we are developing applications for near-term quantum devices, we want to be able to do some realistic simulations to understand the impact of noise on the computations that we want to do on a real quantum computer. So another interesting thing that we could look at would be the simulation time for the same benchmarks that I showed you earlier in the presence of noise. That is when the qubits are interacting with the surroundings. So in general, such simulations are computationally much more involved than ideal simulations. There are few approaches to do such simulations. We could either do them deterministically or stochastically. So in this benchmark, I present the performance that we obtained for deterministic noisy simulations. So such simulations are usually limited to 10 to 15 qubits only because they have a huge memory overhead compared to the ideal simulations. And as you can see, by doing such simulations on a GPU, we could obtain a speed of up to 12 over a 16 core Xeon processor. So far, I've shown you how we could accelerate certain analog quantum computations on GPU. I'm going to finish my part by showing you how we could actually accelerate a full-fledged variational quantum simulation using GPU. These variational quantum algorithms are very important when we work with the so-called noisy intermediate scale quantum computers. This specific use case concerns qubits that are realized with ions trapped linearly, forming a chain as you can see in this figure. Using lasers and magnetic fields, we could make these ions interact with each other, and the couplings between them can be very well controlled. The durations of these couplings can indeed be used as variational parameters. We could then optimize these parameters, for example, to minimize a cost function as explained by Xavier to solve any given problem. This experiment was actually performed for real in a lab in Austria, and they used it to measure the lowest energy state of a problem in particle physics called Schrödinger model. So in the next two slides, I'm going to show you how we could simulate and study this experiment on a classical computer thanks to the GPU. Quantum computers that we have today are intrinsically noisy. By simulating such noisy systems on a classical computer, we can know beforehand whether a variation algorithm can actually work or not if we run it on a real quantum computer. Such studies are extremely important to understand or even adapt the algorithms so that they are noise resilient. Only then we can do something meaningful with the existing quantum computers. Here is an example of how we could simulate the variational algorithm running on a trapped ion qubit system that I showed you earlier in the presence of a very well-controlled noise. The convergence of the variational algorithm is shown in this figure. The strength of the noise is actually set using the parameter called gamma. Here we suppose a very simplified noise model. When gamma is 0, it corresponds to the perfect simulation, that is when there is no noise in the system. And we notice that the cost function approaches the expected ground state energy that we theoretically know. And by increasing the value of the gamma, the cost function doesn't approach the expected result. As we see here, the difference between the expected result and the result given by the variational algorithm increases with the noise. All this study can actually be carried out very fast thanks to our simulator. Finally, I would like to show you an example of a large-scale simulation involving 20 qubits that we performed with our simulator. On the left, we have an experimental result of the variational algorithm implemented using the trapped ions quantum system in Austria. And on the right, we have a simulation of the same experiment reproduced using the GPU accelerated Atos Quantum. I should mention that a 20 qubit trapped ion quantum processor is not yet publicly available in the cloud. Currently, it's only limited to research lab. If one wishes to explore an algorithm of this scale, the only way to do that would be to work on a simulator until the quantum hardware is ready. So in my opinion, such a simulation wouldn't have been possible with the existing open source software packages if we wish to do the simulation in a reasonable amount of time. I hope I have convinced you that quantum computing application development on near-term devices is computationally intensive, and it is quite challenging even on HPC systems. GPUs, with their high number of cores and higher memory bandwidth, can help significantly reduce the development time of new applications. So in this talk, I focused more on accelerating variational algorithms in analog quantum computing using GPUs, but the same is also true in the case of digital quantum computing. GPUs are also very handy for noise modeling of quantum computers because the problems are also computationally quite involved there. And last but not least, GPUs can also emulate quantum annealers or quantum inspired annealers, and which in turn can help solve very large scale combinatorial problems rather quick. So thanks for listening, and I let Xavier finish the session.
Thank you, Satya. As a conclusion, I would like to give you some tracks about how to contribute to this quantum computing initiative. So recently, we have launched MyQLM as a freeware, and so you will find quite easily from Atos website or from Google the documentation that is hosted on GitHub. We have also a bug tracker on GitHub. We are providing a lot of tutorials online that are freely runnable on Binder, which is a cloud version of Jupyter Notebooks. We have a community forum on Slack, and you also can contribute directly by writing your own plugins. And for example, why not a GPU accelerated plugin for MyQLM, and all the links are available here. So just to remind you, what is MyQLM? MyQLM is a full programming environment and simulation and circuit simulation that can interoperate with major frameworks. So some parts of this freeware are proprietary source, some of them are open source, and typically we have a plugin mechanism that allows you to write your own open source plugin, just like Pylinite we are providing. And so if you are interested in evaluating GPU acceleration on quantum simulation or writing other kind of simulator using GPUs, you will be welcome to do so. So thank you again, and don't hesitate to contribute. Thank you. Thank you.